a modeling question in trig. So the depth of the water in a tidal river, which is one whose level is influenced by tides, during a given day is modeled by this equation. T is the number of hours after midnight. Find the minimum depth of the water given by this model. Okay, we just need to think about the minimum value of cos here because we're adding. So the minimum value of cos is -1. So it's going to be 1.9 minus 1.1, giving us 0.8 meters. And then find the value of t when the minimum depth first occurs. So it's going to occurs when cos 30t minus 60 is equal to -1. And that's going to, you can do inverse cos, that's going to be when 30t minus 60 is equal to, I'm just going to look at the cos graph, it's going to equal pi. But we're dealing with degrees here, so 180. Case it's going to be here. I don't know why, it's just easiest probably to put it in your calculator, just make sure it's in degrees. Okay, so what's it? So then 30t is going to be 240, 3t is going to be 24, t is going to be 8 hours. Now, a boat can only enter the river when the depth of the water is at least 1 meter. Determine the 2 periods of time during the day between which this boat will not be able to enter the river. The period where it's lower than 1 meter. Give your answers correct to the nearest minute. So to deal with this, I'm going to find out the times when it's exactly 1 meter. I think it's best to create an equation rather than an inequality. But I might bring the inequality in a bit later on. So then 1.1 cos 30t minus 60 will equal minus 0.9. And cos 30t minus 60 will then equal minus 9 over 11. Okay, and let's do inverse cos minus 9 over 11. Gives 144.903. But that there is here, so we then need to do 360 minus that to get another possible solution. 215.096. Now, how do we know when to stop? Like, it's because there's going to be more solutions. So I just decided to find a couple more, especially because it says find the 2 periods of time. So actually, when I looked at this, I thought, right, this is actually the period where it's below 1, between those two values. So let's add on 360 to each. So 575.096. And then with the 141.44 you actually get 504.903. Okay. Now I'm just going to bring the inequality back in actually. So I want it to be less than 1, so less than 0.9, so less than minus 9 over 11. And you can now see it is going to be between these two intervals here. And then later on, it's going to be between some other intervals. So it's time to work out the values of t in each case, I think. I'm still going to do the equals for the moment, but I'm just going to add 60 on to every value and then divide by 30. And this gives 6.8301, 9.1698. Then for the second two, 18. So we're in the same day, 18.8301. If you did it again, you'd be going to the following day, I think. I think it'd be the exact same time, but anyway, it's going to be outside our range. Then 21 0.1698. So as I said, it's going to be between these two times and between these two times. We just got to work it out as times because it says times in the day. Remember, t at the moment is just a number of hours after midnight. So once you've got your 6.8301, just need to convert it into hours and minutes. It's in hours at the moment. So I would minus 6 and then times by 60. So 6 hours and 50 minutes to the nearest minute. All right, 06. I'm writing 24-hour clock, 50. By the way, I don't know if you knew this, but there is a little function on your calculator that will change it into hours and minutes for you. I never use it, but it's actually pretty good. So as long as you've got hours, minutes, and seconds, if you press this button, it will sort it out. 6 hours, 49 minutes, 48.36 seconds. Great. We just get it like straight away. So you can do it with one of the other ones. 9.1698 equals, and just press this, 9 hours, 10 minutes, and 11 seconds. So it's going to be 9:10. And if you do it for the other ones, you get 6:50 in the evening and then 9:10 at night. In reality, the depth of the river decreases as this boat travels along the river. An improved model uses this equation. So the same thing, but now we're timesing by an exponential term, where c is a positive constant and p is the distance in kilometers traveled along the river after entering it. Explain how this new equation could give an improved model. So it's all about this new term and what's going to happen. As p increases, e to the minus cp will decrease. You can't just say d is going to decrease. You need to quote the exponential here because, otherwise it's kind of intuitive. Because it says the depth is decreasing, that you might say that the new function is going to decrease. You need to quote the exponential. So now I said, so in overall, like d will decrease, but we've got to remember it's still oscillating. So, I kind of want to say it. So d will gradually decrease. I think the mark scheme says amplitudes of peaks will decrease, which is a bit better, I guess, because when you say a function's decreasing, what is actually happening here, you hope, is that you've got this oscillations, but then it's just going to get less and less. So it's still increasing and decreasing, but there's going to obviously be lots of these. It's going to be much more gradual than this, but that's just to illustrate it. So amplitude of peaks will decrease is probably a better thing to do. I think I get away with it just by saying in overall, over the course, it will get closer to the origin, it will decrease, but I think amplitude of peaks is slightly better. Well done.